Hello, students! Let's get started. Today, we're going to tackle a very important topic from Unit 10, Wave Optics, understanding refraction and reflection using something called Huygens Principle. I know, the name sounds a bit complicated, but I promise you, by the end of this short explainer, the idea will be crystal clear and you'll be fully prepared for any exam questions on it. Don't you worry! So, let's start with something you've all seen. You put a pencil in a glass of water, and it looks broken, right? It seems to bend right at the water's surface. It's a kind of magic we see every day, isn't it? Well, by the time we're done today, you'll understand the real physics, the actual reason behind this simple observation. To solve our pencil mystery, we first need to get one idea straight: the wave front. What is it? Just imagine the ripples in a pond. The wave front is simply the line of the crest of the wave. If the wave is coming from very far away, the crests look like straight lines. We call that a plane wavefront. If you just dropped a stone, the crests are circles. That's a spherical wavefront. The main thing to remember is every single point on that line or circle is moving in the exact same way. Okay, now for our superpower for this chapter, Huygens Principle. It sounds fancy, but it's brilliantly simple. There are just 3 steps. Step 1, listen carefully. Every single point on a wavefront behaves like a tiny new source of waves. Step 2, these new sources send out their own little waves, which we call secondary wavelets. And finally, step 3, this is the magic part. The new wavefront, just a moment later, is just the line you can draw that perfectly touches the edge of all these little wavelets. That's it. This is the key to everything. You know, the best way to picture this, the one image you need to remember for your exam is this. Just imagine a long line of soldiers, all marching together on a nice paved road. Now, what do you think happens when this line of soldiers marches into a muddy field at an angle? This simple picture, this is all we need to understand both reflection and refraction. So before we tackle the bending pencil, let's use this new idea on something a bit easier, something we already know pretty well, the law of reflection. This will help us see that our new superpower really works. Ready? Let's go. So, look here. We have a mirror, right? Let's call it XY. And coming towards it is a plane wavefront, AB. You can think of AB as our line of soldiers marching in formation towards a big wall they're about to hit. Now, this is where it gets interesting. The moment the first soldier at point A touches the surface, he starts a new little wave, a wavelet. But hold on, what about the soldier at point B? He's still marching, no? He still has to travel this distance BC to reach the surface. In that exact same time, the wavelet from A has spread out, and since they are moving at the same speed, this is important. The distance BC that soldier B travels is exactly equal to the radius of the wavelet from A. Okay, so now we just use step 3 of Huygens Principle. We draw a line that just touches the wavelet from A and also meets point C. This new line, CD, is our reflected wavefront. Now, just have a look at the 2 triangles we've made, triangle ABC and triangle ADC. You can see they are congruent, right? They share that side AC, they both have a right angle, and we just proved that side BC is equal to side AD. And because the triangles are congruent, what does that mean? It means their angles must be equal. So the angle of incidence, I, is exactly equal to the angle of reflection, R. See? We just proved the law of reflection that you learned in ray optics, but this time using wave theory. Our superpower works! All right, warm-up is over. Now for the main event. Let's finally solve that mystery of the bent pencil. We are going to use our superpower to derive Snell's law and understand exactly why light bends when it goes from air into water. So the setup is a little different now. We have a wavefront, AB, traveling in a rarer medium, like air. Let's say its speed is v1. And it's about to enter a denser medium, like glass, where light actually slows down. Its speed there is v2. This is our soldiers marching from a smooth road right into a muddy field. Now, please pay close attention. This is the most important step. The moment point A enters the glass, what happens? It slows down. It's in the mud. So the little wavelet it creates is smaller. In the same amount of time, T, point B is still on the road, still in the air, so it travels a longer distance BC, which is V1 into T. But the wavelet from A only travels a shorter distance because its speed is only V2. The soldier in the mud is taking smaller steps, you see. And now look at what happens. When we draw the new wavefront, the line that touches this smaller wavelet, the entire wavefront, CD, is forced to bend. It has to rotate. It's so simple, really. Because one end of the line of soldiers slowed down before the other, the whole formation has to turn. It bends towards the normal. And if we just apply a little bit of simple trigonometry to those two right-angled triangles we see on the screen, boom! We get the magic formula n1 sine theta 1 equals n2 sine theta 2. This is Snell's law. So you see, it's not just some rule you have to mug up for the exam. It comes directly, logically, from the fact that light is a wave. Okay, let's put some quick numbers on this so it becomes crystal clear. Let's say light is going from air into glass at an angle of 45 degrees. We just plug the values into Snell's law. 1.0 for air times sine of 45 equals 1.5 for glass times sine of theta 2. You do the calculation, and you find the new angle is just 28.1 degrees. See? The light bent towards normal, exactly like we predicted. It's that simple. Okay, very, very important section coming up now. Let's talk about some silent killers, common mistakes that students make in exams that can cost you marks, so listen carefully. Okay, mistake number 1 is about why light slows down. Many students write that light particles bounce off atoms. Now, that's a very simple picture, and it won't get you full marks. For a complete answer, you need to say this. Light is an electromagnetic wave. It makes the charges inside the atoms of the medium vibrate. These vibrating charges then re-emit the wave, and this whole process, this interaction and re-emission, is what causes the overall wave to travel slower. That's the full marks answer. Another point of confusion is, which way does the light bend? Don't get confused, just remember our soldiers. When they enter the mud, they slow down and bend towards the normal. And if they were coming out of the mud, back onto the road, they would speed up and bend away from the normal. It's all about the speed change. Slower means towards, faster means away. Simple as that. And this is the big connection, the aha moment. Your previous chapter, ray optics, it told you what happens. It gave you Snell's law as a rule. But this chapter, wave optics, with Huygens Principle, it tells you why it happens. It's the difference between just knowing a formula and truly understanding the physics behind it. Okay, let's do a quick revision summary before we finish. Just remember these 4 key points for your exam, and you will be sorted. Point number 1, both reflection and refraction laws can be derived from Huygens Principle. 2, the main reason for refraction is the change in the speed of light as it goes from one medium to another. 3, and this is a very common exam question, when light refracts, its speed and wavelength change, but its frequency, that stays constant. And finally, number 4, this same principle also explains amazing things like total internal reflection, which is the secret behind how fiber optics work. So today we learned why light bends, but let me leave you with one final question to think about. What if we could design a special material that makes light bend backwards? I know it sounds like something from a movie, but this is a real area of physics research. It's what could lead to things like invisibility cloaks. Something to think about, isn't it? Okay, that's all for today.